Welcome to lecture 34 regarding the data labels for different simulations and discuss of the statistical technique used for the calibration and validation of the model performance. So, last lecture as we discussed we have model performance files. So, that is a file and T file. A file particularly single stage events like maximum leaf index, biomass at maturity or biomass at flowering, or you can say the grain yield grams per meter square, or the biomass at maturity as gram per kg per hectare. These single stage events, this is A file, and T file is time series events like leaf index throughout the growing periods. That changes over time, and number of tillers per meter square, that also changes over time. So, these are the biomass or the leaf biomass from starting from the planting to maturity, that changes over time as the leaf biomass, root biomass, stem biomass. So, these are the time series events. So, this time series data and the A data, the single stage event data, they are the input to the crop models, and this is used for the model calibrations of the model parameters and also evaluation of the model performance. So, we will discuss this one, what are the data labels used for the different operations in the models. So, data label for the simulations, label 1, you need the minimum data to run the models. So, what are the data label for the minimum data requirement to run the models? Then label 2 is the data to evaluate and calibrate models. So, as you discussed the model performance in file, that is input file, that is must for the evaluation and calibration of the model parameters. But for only to run the model, you need the minimum data set. In that case, the model performance file not be required for the run the model. So, we discuss what are the files required for the to run the model, label 1, then to evaluate the model, label 2, then for development of model, label 3. So, these are the 3 levels of the simulations we can do. The label 1 is the minimum data set to run the model, label 2 data set for the evaluation for the model performance, and label 3 the data for the model development. So, in this case, see the we will dealing with the label 1, label 2, label 3 that needs a data set model development. This needs all experimental data as we are discussing the previous beginning classes. So, depending upon your the objectives of the model development, accordingly the experiment hypothesis experiment is established or created to generate data to meet the objective of the model. So, that the model development we are not looking for, this is a scientific goal of this crop modeling and simulations. We will be dealing with the label 1 and label 2. So, for label 1, the minimum data required to run the model, the daily weather, the maximum temperature, minimum temperature, rainfall and radiation, then soil surface and the profile data as we discussed. This is soil data, physical properties, chemical properties, layer wise those information required. Crops and cultivar. So, cultivar coefficients, particularly particular crop and its cultivar, what type of variety is used, genotype coefficient that is required, and the experimental management from the land preparations to continuing for the seeding operations, nutrient management, irrigation management, plant protection measures. So, these are the operations that is used for the as a management files. So, these are the 4 files for the as input to the crop model, and this 4 file is required for running or the simulation exercise. So, this is a minimum data set required for operation of a model or the for simulation of any crop model. You go for simulation output, you need these 4 minimum data sets, that is a must. Daily weather, T max, T mean, rainfall, radiation, weather data, soil characteristic, soil surface and the profile layers, physical and chemical properties, then cultivar coefficient, say crop, particular crop and genotype coefficients as per the crop specific, then your experimental managements. So, these are the 4 data sets required for the operation of the model or running models. Label 2, label 2 that is for the as a model performance evaluations. For label 2, you require all the data of label 1 in addition to this. These are the additional data requirement that is phenology dates, means the crop physiological growth stages, appearance of different growth stages like tillering or the panicle initiations in case of rice, then flowering, then grain filling, maturity. So, these are the phenological events. So, those information as a say as a crop performance file, as we discussed earlier, crop performance file, that is added in addition to the minimum data set for the label 2 for model performance evaluations. That is a phenology dates, biomass components, root biomass, leaf biomass, stem biomass, regular time series, the biomass components, yield and yield components of the crops, final grain yield and yield components. Yield in case of rice, if say example, that it becomes panicles per meter square, grains per panicle, single grain weight. So, the field grain percentage, these are the yield components, and the grain yield, these are the inputs to the crop model for the label 2 operations. So, these are the two labels we are dealing. Label 1, the minimum data set for the model operations, and label 2, the additional data set we put in addition to the label 1 for the model performance evaluations. The purpose of this calibration, we are discussing how the model performance evaluation means, that becomes calibration, validation of the model parameters. The crop models must be evaluated. The calibration means the adjustment of the parameters, change of the parameters to have a best fit between the simulated and the observed value, that is how say calibrations. Validation is the test the model performance with the unknown or the independent data set, we can say, that is the validations. So, initially we use some type of experimental data or the crop performance data for calibrating model parameters to have a best match between the simulated and the observed value. Once you calibrate the model parameter, then use that model for another sets of experiment. The data of that experiment must not be used for the calibration process. So, if you so whatever data crop data that is used for the model validations, model evaluation, model performance evaluations. Okay. So, that is what the validation test model performance is on independent data sets. So, this is the purpose of calibration, because once you have the model validation is good, then you can apply the model for different scenarios. So, we will discuss what are the statistical techniques are used for the calibrations and this validations of the model performance. These are the data set used. You have got the simulated values. So, you have the observed values, then mean of the observed values, number of observations. This applied to for the yield simulations, biomass simulation, phenology, leaf area index. So, because once you have the crop growth, then you have the soil water balance simulation, nitrogen dynamics, carbon dynamics, of course, these are all simulated using this model. So, what are the statistical parameter used matrix? One is the root mean square error. Root mean square error is equal to 1 by n number of observations, that is Si is the simulated value, Oi is the observed value. Already you have discussed here, we have Si the simulated value data required, observed value, the mean of the observed value, n number of observations. So, these are the Si the simulated value, Oi the observed value, square, then we are taking the root. So, say root mean square. So, this is used to, this gives the error between the simulations and the observed values. So, how to do it? Because now if you calculate this root mean square error, for example, I can give you here. In case you are using models, you are simulating yield, crop yield for for a particular locations for different conditions. You have applied the models. You want to compare the relations or the difference between the simulated value and observed value, whether they are the close match or they are differ very widely differ. Suppose the observed yield kg per hectare and this is simulated value. And the value 1000, 4000, 8000, 10,000. This is also 1,000, 4,000, 8,000, 10,000. And this is 1:1 line. If the line, if the observed value is same as the simulated value, the points will fall on all the points will fall on 1:1 line. But this this does not happen in case of the experiments. Not exactly the observed value, whatever the value got from the experimental value, that will remain same as the simulation value. The value may disperse, may be seen around this 1:1 line. So, this so these are data points. Suppose you have 1, 2, 3, 4, 5, 6 observations. So, 6 data points you have you are looking at you have experimental yield and same in information given for the model for simulations, we have got simulated yield. So, we calculate the root mean square error for this value. What is this is the observed yield, this is the simulated yield. For this value, this is the observed yield, the simulated yield. For this value, this is the observed yield, this is the simulated yield. For this point, this is the observed yield, the simulated yield. So, every point you have the observed value and simulated value. So, you calculate the root mean square error using these simulated data points and the observed data points. We calculate this root mean square error, that gives the indication the error from between the simulation and the observed output. So, this is the root mean square error. Similarly, also we do calculate this normalized root mean square error. Normalized root mean square error, that gives RMSE, this is RMSE n is equal to RMSE by mean of observation into 100. So, for this this gives a percentage error between the simulation and the observed values. So, if you have the 6 data points, you know what is the mean of the value. Suppose you are given rice yield, suppose O bar is equal to mean is around 4,000 kg per hectare, the mean yield, and the error is root mean square, the root mean square error RMSE is equal to 100 kg per hectare. So, you can calculate RMSE n (100) by 4,000 converted into percentage. How much percentage? So, likewise, this is the normalized root mean square error. So, this can be converted as a percent, how much 100 by 4,000 into percentage, this gives the percentage of this error. So, this indicates the error percentage between the observed and this simulation output. So, that so instead of root mean square error, that gives a particular value only, but when you go for the root mean square error normalized, that gives error as compared to the observed value or experimental value. This gives a more realistic value informations about the simulations, how far this simulation value, how far from the observed value. So, our purpose is how to bring close. If they are the same, then the RMSE becomes 0, because if they are because simulation value becomes same as observed value. So, there is no error, RMSE becomes 0, root mean square error becomes 0, but in reality this never happens. So, there is some error, we have to need to calculate. So, how much error? So, that will guide us how you can go for the calibration of the model parameter to have a best match, best fit between the simulation and observed output, so that we can minimize the error. The idea is calibration validations to minimize the error in the model. So, this is the root mean square error. Similarly, we calculate the mean error. Mean error is mean error, that is a 1 minus this this is only the as per the value, some simulation value minus observed value by number of observations, or if take mean absolute error irrespective of the sign, we can take the simulation minus observed value and we can get mean absolute error. So, these are the this used for the as a testing for the model performance, and the other one index of agreement, say D stat. D stat, D is equal to 1 minus SI minus OI square by summation of the SI plus OI square. What this SI is the SI minus O bar plus OI minus O bar square. SI is the simulated value, OI is the observed value, O bar is the mean of observation, the O bar is the mean of observations. So, D index or the index of agreement, that is 1 minus SI minus Y square by SI minus O bar plus OI minus O bar square. Okay. So, the when there is simulation and observed values remain same, this D index becomes 1. As for the error, the D index varies from 0 to 1. 1 means there is a good agreement, that means the simulation is same as the observations, but this of course, this usually does not happen in case of the field experiment. There is some difference between the simulation value and observed value. So, based upon that we calculate the D value, we can say the index of agreement. So, D value this varies from 0 is more than higher than 0.8, that means it is a very good performance. This model is we calculate when you go for the calibration and the validations. I think you remember, if the beginning some class I have discussed in case calibration where you make the adjustment of model parameters. In case I am going for the biomass simulation time series or the grain yield, as you have discussed grain yield also, or time series biomass, model simulates time and this biomass. Gram per meter square. So, model simulates the biomass as per the crop growth curve, is the model simulation. The x axis, the y axis, and these are the model simulate the solid line that indicate the model simulations. And suppose you have the observed points somewhere, you have taken few observed points. So, these are your observed points. These are observed points. So, there is a gap between the model the points of the observed value, and at that point what is the simulated value. These are the gap, each point there is a gap. So, this gap, this is due to the difference between simulation and observed. So, to minimize the gap, what we do, we go for the calibration model parameter. So, the purpose of calibration means you cannot change the observed value. So, we want to bring the simulation value very close to observed value. So, this point may be shifted like this the simulation value to be shifted, so that we can get the simulation value very closer to the observed data points. We do that calibration, through that the simulation value gets shifted to the very close to the observed value. So, that is the process of calibration. In calibration, we do change the model parameters, the process of calibration, but validation is the testing of model parameters. So, D index or D stat we are using for calibration process. For calibration, D stat should be greater than 0.9. For calibration, the D value, D stat should be greater than equal to 0.90. because in calibration you are changing these model parameters to have a best match between the simulated and observed outputs. In that case, the d value should be must 0.9 or higher than 0.9. For validations, since you are testing the model performance with a unknown data set, in that case that will indicate the calibration process, the validity of the calibration can be indicated through validation process. If during validations the d value is greater than 0.8, we can say is a model is performing very well. Model performance is very good, that evaluate during the process. This is for the process of validation. For calibration, the d star should be 0.9 or higher must. For validations, if the d value is greater than 0.8 is a good performance model, d is equal to 0.5 moderate agreement, d less than 0.5 poor simulations. Usually we say that for validations we can accept also, but it should be d value should be at least more than 0.6. 0.8 is a very good, if you get d value 0.8 higher, that means the model performance is very consistent, the calibration process is perfect, the model is able to simulate the actual yield that is observed through field experiments, if the d value is higher than 0.8 during validation process. And this 0.5 is only moderate agreement, moderate good agreement, less than 0.5 we may not accept the model, that indicates for the recalibration of model parameters. If you are getting the poor simulations, model is unable to reflect the reality or the actual field experimental conditions, then we have to go for the recalibration of the model parameters. Model parameters probably is not calibrated well, so that can be applied to any unknown conditions for the better for the simulations. So, this is how you go for the statistical analysis that guides you for the calibration process. So, what we are discussing the DSAT, we have discussed the input file, the input naming files, and the calibration validation process. Calibration is the change of parameters to have a best match between the simulation and the observed outputs, and validation you are testing the model performance using a unknown data set, and validation guides you that the performance of the models, and for that we need that the performance files, the crop file, the performance files, that's as input for the crop models, and through this performance file we go for the calibration and validation of the model parameters using this statistical technique. And particularly if you go for the normalized root mean square error during validations, it should be higher than error is less than 10%, it is excellent, you can say model is performing very well, or 20%, if the error is 50% error, then this is a very poor simulations, you can say, then you go for the recalibrations. So, these are the as a for the calibration and validations of the model performance. Can say from this you can say this error statistics quantify DSAT simulations accuracy and the reliability, and the root mean square error and the mean absolute error represent the error magnitude, while mean error indicate the systematic bias in the model. DSAT assess the model agreement and the predictive efficiency, because DSAT is used to see the for calibration, the DSAT value should be definitely 0.9 or higher for calibrations, and for validations if a DSAT value that assess the agreement and this is very poor, then you go for the recalibrations of these model parameters. And this is a reliable DSAT validation requires combined interpretation of all matrices, because you can use the root mean square error, you can use root mean square error normalized, you can use also DSAT. So, that gives information about the model performance evaluations. So, for the you need that for this you need the label 1 data set, that is the weather parameters, soil parameters, cultivar parameters and management, particularly for the label 1 for the running the models. In addition to the label 1 data sets, you need the crop informations, crop performance informations, the phenological events, the flowering, the tillering, as per the crop wise the phenological events, and the crop wise the biomass, the growth outputs and the yield components and the yield outputs, those information required for the model performance evaluations. Once you put that input and go for the statistical technique and to make confirmations that model is now well validated, now the model can be used for any scenario analysis or for the what if scenarios, and to have a decision making process, the model can be applied for the different conditions and to for the recommendations or the management decision. So, this is what for the statistical technique for the model calibration and validations. With this, I thank you all.